So welcome to this lecture on programmable logic devices in the course Digital System Design with PLDs and FPGAs. We have completed our advanced digital design part. I have covered almost everything: data path design, controller design, issues in the controller design, then some essential topics on synchronization, top down design. Everything is completed. VHDL we have as far as the synthesis is concerned, we have completed everything pretty much. What is remaining is maybe the test benches we have to cover to write the test bench for simulation. We will do that, and two topics are left. One is programmable logic devices and field programmable gate arrays, and we will next few lectures we will try to complete the programmable logic devices or PLDs. And I must tell you that there are two types of devices in this PLDs. One is SPLDs and CPLDs. One is simple programmable logic devices, and the second one is complex programmable logic devices. SPLDs are very rarely used, but it is better for an academic interest to go through that part, so that when it comes to the CPLD it is very easy to understand, and also maybe that gives you a little bit of how these devices are evolved. Maybe it's useful. I mean, I'm not very sure about it, but CPLDs have some use at least. It's not as useful as FPGAs, because nowadays the designs are very complex and people try to build a lot of things into a single chip. To that extent CPLDs are not much used, but they do have a place in the case of low and medium complexity design, and they have some advantages, some disadvantages, which we will see. So let us start with the programmable logic devices. So let us look at the slides. So we are going to hold together the programmable logic devices, which are called PLDs, and as I said there are two parts. One is SPLD and CPLD. Basic idea is now when you look at the evolution, this has started, this idea of the programmable logic devices has started quite some time back, maybe 25 to 30 years back, and there were I mean the VLSI circuit density was not much. People needed some kind of programmable logic, and earlier designers used to work with discrete gates and discrete functions like multiplexers, demultiplexers, encoder, decoder. So when you had normally a logic design, it was a printed circuit board full of small integrated circuits, okay, which was not very complex. You know, you will have some gates, you will have some multiplexers, encoders, decoders. As we have the design was pretty much same what we have seen, but it was implemented not in a single chip, plenty of chips. It was huge number of chips, okay. So you should when we talk about the evolution, you should think of that scenario, not today's scenario. So there was some need of programmable logic. The first thing comes to mind is the chip select decoding in a microprocessor based design. That means in a microprocessor you have lot of memory and peripherals. Again, in those days it was not a single chip. There will be multiple memory chips to cover the memory space, multiple peripherals. All these need some kind of the memory map. Everything is mapped to the memory map of the processor, and that is done by the chip select decoding by the higher address bits, and that some kind of flexibility was required in kind of mapping these devices into appropriate places depending on the need. Okay. So there was, at least for chip select decoding, there was some kind of programmability was required. So I think that was a kind of starting point of this programmable logic. So the only programmable element then available was memories. Okay. What is called programmable read only memories. So that's a context. So basically the idea, coming back to the slide, the idea is how to use memory as some programmable logic, like you have standard memory, how to use it as a programmable logic. That was a basic idea. So let us clear that part so that you are kind of not lost in all the old technology, because if I show a picture of one of the PROM kind of architecture, then you will be wondering what is going on. So let us treat this idea. Suppose we take a two variables x and y, and you want to implement this Boolean function of x and y, which is nothing but x XOR y. Okay. So don't confuse with this these two x's. This is the variable, this is a function, and this is y. Okay. Now idea is how to use a memory to implement this x XOR y. That's a basic idea, and we take a two address line memory, that means 4 location it has, and that means we take a 4 into 1 memory, and you know that there are 4 location, and when address line is 0 0, the 0th location is selected, address line is 1 0 1 first, 1 0 second, and 1 1 third location. Okay. So internally there is an address decoder, depending on the value you put here, appropriate location is selected, okay, for writing or reading. Now assume the truth table of x XOR y is programmed in this 4 location. Okay. So basically x XOR y is the function is either of the input is 1, then the output is 1. So if both inputs are 0, that value is 0, 0 1, that means this is x bar y is 1, x y bar is 1, x y is 0. Okay. So what we are doing is that we are programming that the truth table into these 4 locations, because these are 2 address lines are connected to these variables. Okay. And this is somehow programmed. Okay. We just write that truth table into these locations. Now you check what happens. Suppose we give 0 0 as the input value. Now that writing is kind of part of the programming this memory with the truth table, and when you want to kind of use it as a logic, what you do is that you put this memory in the read mode. So I am not showing that, I have assumed that it is written and this is already in the read mode. Okay. So the logic works when the memory is in the read mode. When the memory is in the write mode, we write the truth table. Okay. And I am not showing the writing part, which is understood. So if you give 0 0 to x and y, then this 0th location 0 0 location is accessed and you get a 0 here, and if it is 0 1, it accesses this location, and then 1 comes on the data line. So the data line is the output, address line is the input, and again you give 1 0, the 1 comes here, 1 1 0 comes here. So basically you take a memory of the required capacity. That means suppose you have you want to implement a 5 variable function, then you take a memory with 5 address line or 32 locations into 1 bit, 1 data line we require, connect all the variables to the address line, 5 variables to 5 address line in whichever order, it does not matter, but then you have to appropriately program the truth table. Okay. So you program the truth table, then use the data line as a Boolean function, the output of that logic, that is what is required. So that is how we use the memory as a kind of programmable logic. Address lines are the inputs, data line as the output. This is while working as logic. Truth table is the content. Of course when you write the truth table into this memory, then this data line is definitely the input, okay, is not the output, okay. But in operation, when the logic is in operation, address line is the input, data line is the output. Now if you use a kind of static RAM which is kind of volatile, each time you power up the locations are not defined, okay. We don't know what is the content of the location, it could be 0 or 1 because these are kind of the latches inside. SRAM cells are nothing but kind of cross coupled latches which will come up with some random values. So you have to write. So you cannot use SRAM as a programmable logic. You can use, but you have to write it each time. But so if you once again go back to the old scenario, that was not kind of possible, and so some kind of non-volatility was required. That means you program it once for all maybe, but then it should retain this truth table inside, okay. So such a device was available then, that is called programmable read only memories or called PROM, okay. So the architecture of the PROM was like this, and we are showing now exactly similar one. That means 4 locations, 2 address line. Instead of 1 data bit I am showing 2 data bit, that is the only difference. So this was the architecture of the PROM or programmable read only memory, okay. So that is called programmable read only memory. That means you can, once you program it, you can only read it, you cannot write it. So you can say it's a write once and read many times memory or something like that. So you have here a 4 location memory with 2 bits output, and if you see there are 2 address line A1 and A0. A1 and this is a complement of that, A0 complement of that, and this part is the address decoder. So this line when both are 0 0, A1 bar A0 bar, this AND gate is 1, this is A1 bar and A0, this is 1. So it chooses, these are the min terms, and A1 A0 bar A1 A0. So these 4 AND gates are the 4 locations, okay. Now take one data line and there are connections, okay, like there is a diode and a fuse, and this is a normal fuse which can be blown by passing a larger current, okay. So there are 4 connections through diode, and we will see why the diode is required. I mean, this is, we are discussing the old architecture, and this data line is pulled down to the ground through a resistance, and this is the output, okay. If you need a buffer, you can imagine a buffer here, and similarly any number of outputs can be there which allows you to implement multiple outputs, okay. Now assume you want to program your XOR function, that means 0 1 1 0, okay. Now what you do is that you blow the fuse, we will see how to blow the fuse. You just blow this fuse, retain this connection and blow the fuse, okay. So it is equivalent to programming 0 1 1 0, exactly like here 0 1 1 0, because we are trying to implement the XOR of the input, okay. So here we have 2 inputs, you can assume it is X and Y. Now like if you program 0 1 1 0, you see what happens, you give 0 0 here, then this AND gate is 1 and rest all is 0, okay. So the moment it is 0, these diodes won't conduct, okay, and this is 1 but you see that this fuse is blown, okay. So this, there is no conduction here and it is pulled down, you get a 0. So but if it is kind of 0 1 then this AND gate output is 1, rest are 0. So since this is 1 and this is pulled low, this diode will conduct, the fuse is retained, so you get a 1. Similarly when you have 1 0, this diode will conduct, the fuse is intact and you get a 1, and when it is 1 1, this is active, rest all are 0, but this fuse is blown, so it won't conduct, it is pulled low and then you get this, okay. So you can say that this is acting like a programmable OR, okay. So we are programming the OR function, you can imagine this as an AND and an OR, okay. So this is a fixed AND, you have 2 inputs, so you have 2 raised to 2 min terms, A1 bar A0 bar, A1 bar A0, A1 A0 bar and A1 A0, all the min terms are there. So suppose you have n inputs, then you can imagine there will be 2n vertical lines, n inputs and their complements, and there will be 2 raised to n AND gates here. Each AND gate will have n inputs, okay, because you need to choose an input or its complement. So for an n input case there will be 2n vertical lines representing n inputs and its complement, and there will be 2 raised to n AND gates representing all the min terms, and there are each AND gate there will be n inputs selecting the appropriate min term, okay. Now you program the truth table by blowing the fuse, okay. Now the next, before we see how to blow the fuse, what is the purpose of this diode, okay. You might be wondering why a diode is required, because it is definitely not to do anything to do with the 0, because when you want to program a 0 you blow the fuse, there is no connection at all. So it has something to do with the connections you are retaining. So in the case of XOR gate we have programmed 0, 1, 1 and 0, that means these 2 fuses are blown, they are not there, these 2 are retained, okay. Assume the input is 1 0, okay. When the input is 1 0, the AND gate, this AND gate is high 1 and this AND gate is low 0. Suppose there is no diode, there is a direct connection, then you can imagine that what happens, then there is a direct connection through the fuse, one output is 1, other output is 0. So there will be a short circuit directly from the VCC to ground, the VCC of this through the PMOS, or then maybe earlier it was kind of BJTs used, but does not matter, but then there will be a from the VCC it is coming through that and it goes to the ground through the transistor pulling low, so there is a short circuit. So this diode kind of block that zeros, so that there is no direct conduction between the VCC and the ground. So if this is kind of 1 0, then this is 1, this and this, since it is pulled low, this diode will conduct, the 1 reaches here, but since this is a reverse bias, this diode is, this 1 is here and the 1 is here, it is reverse bias, you need to have at least 0.7 volt difference. Being identical gates, that cannot happen, and so this will not conduct, this will not create short circuit. That is the idea of the diode. So as I said, the programmable read only memory is a kind of fixed and a programmable OR, okay. Now how to blow the fuse, it is enough if like if the current rating is say 20 milliampere, you draw larger current, maybe the 30 milliampere or 40 milliampere, then this fuse is blown. It is a one time business. What is done is that at this point, okay, suppose you want to blow this fuse, and naturally this has to source that current, there will be some mechanism to source a larger current wherever you are connecting that output is there will be large current sourcing. So say you want to blow the fuse, what is done is that you give 0 0 here. Now what you do is that take this point and apply a negative voltage, maybe say this is grounded, so you give kind of minus 5 volt and the supply is 5 volt. Earlier the potential difference was somewhere around 5 volt, little less than 5 volt. Now it will be near around 9 volt because it is a double with some drops removed or near to the 10 volt. So the current flowing through the fuse is double that of the normal current and it will blow the fuse, and it just for a short duration a negative pulse is applied. And if you care to see the old time devices, there is a pin called VPP, that is called the programming voltage. V is the voltage, P is the programming. So there you apply a negative voltage and then you can appropriately choosing the min term you can blow the fuse, rest will be retained. But as I said it's a kind of non-volatile, once you program you cannot reprogram it, then you get it, okay. So that was the basic idea of the programmable read-only memory. You can implement a combination circuit, essentially you program the truth table, and we have seen that it is a fixed AND and it's a programmable OR, okay. The AND is fixed by this 2 raised to n AND gates in the case of n inputs. By blowing or retaining the fuses we are programming 0 or 1, so you are able to program the truth table. And also like when in the case of multiple outputs, like in this case 2 output, a same min term can be chosen, okay. You can share a min term between 2 outputs, and it's possible that the first output may not use that min term, the second output may use, or both may use, but in any case it's possible that a single min term can be shared between 2 outputs, that's possible, okay. So that is the idea, but basically there is a problem. As you go increase the number of inputs, say assume that in a chip select decoding maybe you have to kind of use say decode 10 address line, okay. Suppose there was a 16-bit microprocessor, then only say A15 to A9 need to be, or A6 need to be decoded, that means 10 address line need to be decoded. Then you will have 10 address line and 2 raised to 10 1024 locations, that means 1024 AND gates, okay. Now it's really funny if you look at the particular application of chip select decoding. You are mapping the device to a particular location, and many a times it require only one AND gate, okay. Like say all the higher address bits are 1 1 or some pattern, okay. Many a times you require only one AND gate, but you have 1024 AND gates. So these AND gates for many, like that even if in a 5 variable normal boolean function, you are not going to use 2 raised to 5 min terms, okay. If you use all the min terms then the output is 1 always. So this is an overkill, this number of AND gates are overkill. So the question we are asking is that can we reduce the number of AND gates, okay. So that was a natural question people asked. So it all started with designers using the PROM as a programmable logic, which was not kind of intended function of the PROM, though it is obvious for us now. That time it was a kind of invention or a creative use of the PROM. So people felt that actually there is a lot of wastage of the AND gate in this kind of architecture. So why don't we use less number of AND gates? The moment you use less number of AND gates, then you should realize that those AND gates we cannot fix the min terms, okay. Suppose we say that let us remove these 2 AND gates, then what happens is that you have only minterms A1 bar A0 bar and A1 bar A0 is available. Then we wouldn't be able to program the XOR function. Okay. So the moment you try to reduce the number of AND gates, then you should make sure that these AND gates are programmable. That means these minterms should be programmable. That means you should be, instead of two fixed connection with an AND gate with 2 input, you should have an AND gate with 4 input and with maybe fuses connected at the input, some kind of programmable mechanism. We will see what is that mechanism, how it is really implemented. This is just a kind of logical schematic, not the actual implementation, and we will see how this is implemented using transistors. We will see that, but essentially it require AND gates with 4 inputs, 4 programmable inputs. Then we can reduce, we can have only using some statistics, okay, like you study the Boolean function of different variables, 5 variables, 6 variables from practical cases, and say in 90% of 80% of the time for a 5 input scenario you don't require more than say 14 minterms or something like that, then you can use only 14 AND gates. Okay. Now the moment you introduce the programmability in the AND gate, it's even possible, there is another advantage, that you don't need to kind of stick on with the minterms. Now you can stick on with the product terms. Okay. So earlier suppose we had used A1 bar A0 bar and A1 bar A0. Okay. So both minterms were there, but we know that A1 bar A0 or A1 bar A0 bar or A1 bar A0 is nothing but A1 bar only. So it's possible that in such a scenario you can minimize your Boolean equation, okay, and the product term, now if you have 2 minterms in the output, then what you do is that you only implement A1 bar here. That means you there are 4 connections, you retain the A1 bar connection and blow all the other connections. Okay. So the moment you have lesser, moment we decide we can use lesser number of AND gates, we would definitely make these AND gates programmable, and at that point we don't need any more, we are not working with the minterms, we will work with the product terms, which will even reduce the requirement of number of AND gates. Okay. So that was the next step. Okay. People started building these devices, okay, from idea taken from this PROM that this is too much of an overkill. For most applications doesn't require these number of AND gates. For chip select decoding it's very few, 1 AND gate or 2 AND gates, and even in normal Boolean function the number of AND gates required are less. So people reduce the number of AND gates but made the AND gates programmable, and the moment it is programmable the requirement of minterms has vanished and we have come to the product term. So essentially you kind of minimize your equation and start implementing it that. So that's what we said, we can reduce the AND gate but the AND gate should be programmable, the minterms become the product terms, and such a device was called PLA. Okay. The programmable logic array it was called, it is called programmable logic array. Okay. I'm sorry that I have not written that in the previous slide. So the programmable logic array, now somewhere in the lecture I have told don't worry too much about these terminologies. I mean, don't ask me why it is called programmable logic array. I mean just a name, it may have some kind of justification by those who invented it, but we need not worry too much about these terminologies because all the more we go to the next step it will be kind of confusing. So this was the architecture of programmable logic array. Again we are taking the case of 2 input case where there are 2 inputs and its complement. Now instead of 2 raised to 2 AND gates we have only 2 AND gates, and each AND gate has the 4 inputs to connect to the 2 inputs and its complement with a programmability with a fuse, with some kind of programmability, like in the simplest case you can imagine it's a fuse and you want to program say A1 bar, then you retain this fuse, blow all other fuse, or you want A1 bar A0, then you retain these 2 fuse and remove this fuse, and naturally you can do the programmable OR. Okay, now this become pretty much complicated because if you have multiple outputs, what to program, how to program this, because now when you have multiple output it's possible that a single product term can be shared between the output. Now we have talked a little bit about the multi-output minimization when we have done an overview of at the beginning of the course, and when you have a multi-output minimization you have to find basically the common sub expression in the equation and try to implement that. Okay, that is what need to be done here. What is common, the largest common sub expression should be implemented, and that can be shared between these two, but you see that this is a little bit of an overkill because there is a lot of programmability now. Okay, now like you have like you have programmable AND and programmable OR. Okay, so summarizing, you have the PLA was a programmable AND and a programmable OR. The prom was fixed AND because all the minterms were there, and the programmable OR. When it comes to programmable logic array, you have the programmable AND and programmable OR. We have less than 2 raised to n product terms, and you can share the product terms by output, and there is tremendous programming overhead because you have to kind of program these fuses at the input of the AND gate and the output of the AND gate and so on. A lot of programming overhead was there, but much more than that. Suppose you assume a single output, don't worry about multiple output scenario, you just take a single output, you are able to program whatever the product term you require. The moment you do that, there is a less requirement, less need for a programmable R or kind of thing. Okay, because suppose you are trying to program X XOR Y, okay, or A XOR B, like A is connected here, B is connected here, then we will program A bar B here, A B bar here. There is no need to kind of program this. Okay, so assume there are 4 AND gates. Okay, and if somehow you can disable these 2 AND gates, then there is no need to kind of somehow you make the output of the AND gate 0, then there is no need for this programmable OR section. We can fix, make the connection fix, and that will make all the programming overhead reduce. So that is that was the next evolution. For a single output you don't need a programmable OR, because if you have multiple AND gates, suppose in this case we have put 3 AND gates and you need only 2 product terms, somehow make the AND gate output 0, we will see that how to do that. Then there is no need to have a programmable OR section at the output. That was the basic idea, and such a device is called programmable array logic. Okay, now this was programmable logic array and this was programmable array logic, and there is, as I said, don't worry too much about the name. Okay, one is called PLA and another is called PAL. So it's kind of programmable logic, but since earlier one was called PLA, this was called PAL, and now I will kind of use a shorthand for representing the AND gate. So let us come to PLA. Now onwards it's very difficult, like when we are going to see some practical devices which has lot of inputs. Now in a picture, if there are say 10 inputs, then we will have 20 vertical lines, and it's very difficult to show AND gate with all the 20 connections. So now what we are going to in the next slide onwards, when we have a 4 input AND gate, we will only show a single line going like that. Assume that there is programmability at the cross point. Okay. So we are going to show, so like this, you have an AND gate, a single line, assume that there is a programmability, assume that this is a 4 input AND gate. Okay, that is the best way to do that. We will see how it is implemented, as I said. So we have a shorthand representation of a 4 input AND gate with programmability at all these inputs. Okay. So this is the kind of architecture of programmable array logic, wherein you have some fixed number of programmable AND gates. In this case there are 3 AND gates which is permanently connected to an OR gate. Okay. So when you take this output, you can program, you can implement a Boolean function of 2 variables up to 3 product terms. Okay, up to, like you have only one product term that will be programmed in the first AND gate, and somehow we make sure that this AND gates and this AND gates are disabled. Okay, we will see that how to do that very a simple and elegant way. So this is the architecture of programmable array logic, wherein the AND gates are programmable but the number of AND gates are fixed. The OR gate is fixed, that means if we have 3 AND gates which is connected to an OR gate permanently, and you get an output. And maybe like in a real device there could be variation, like it is not that all the outputs are kind of consist of 3 product terms, maybe there are some output which consists of only 2 product terms and things like that. Okay. So that is how, and this is the basic architecture of a PLD or programmable logic devices. Okay. The PAL is the real architecture of the programmable logic devices, and we were talking about the evolution and the real kind of logical reasoning behind how this has evolved. Okay. So though we are not using any of those very much, definitely we are not using the PROM and the PLAs, and the PALs are used, but then it is a worthwhile academic exercise how this is evolved and why such an evolution happened. Okay. To understand that will help in some other logic design, I hope. So the PAL is programmable and fixed OR. So we started with a programmable fixed and a programmable OR. We have come to both programmable, then we have kind of inverted it. It was from a fixed and programmable OR, we have ended up with a programmable and fixed OR for all the reason we have stated. So here you have for an n input you have 2 raised to less than 2 raised to n product terms. Each AND gate of the product term has 2 n inputs. To be able to program any min term or a product term, you have a dedicated product term for output, and for a particular output the product terms are fixed. Okay, that is the architecture of the PAL. So this is the evolution. We have started with the PROM, which is programmable read only memory, which had basically a real memory where the address decoder acts as a min terms of the Boolean function fixed AND. So n input you have 2 raised to n AND gates, each AND gate has fixed connection to the n lines. Then a programmable OR, basically it works as programming the location with truth table, and in a PROM that is implemented, that programmability is implemented through the fuses which we blow by blowing flowing a large current, and diodes are kind of in series, not kind of a cross drive from the VCC to the ground. The next one was that this AND was an overkill, because in a chip select decoding very few AND gates are used, only one AND gate is used. Even in real Boolean function the number of the product term min terms are less, so we reduced the number of AND gates, but then it necessitated to make it programmable, that means increasing the number of inputs to 2n, and which is programmable, and that enable not only the min terms, the product terms, which was much more kind of useful. It allowed to reduce the number of the AND gates, because the moment you talk about the product term you are talking about minimized implementation. The Boolean equation is minimized to get the product terms that is implemented, and the programmable OR, lot of overhead because of programmable OR. Again, for a single output we said that this programmable OR doesn't make sense, because we program whatever the product terms we require and disable the AND gates that automatically implement the programmable OR. So it was possible to kind of fix the OR, and by playing with the AND gates, disabling the AND gates, we could get that programmability in the kind of in the present day language. We can say we can get a virtual programmable OR or something like that. So that prompted this particular architecture, the PAL, which has a programmable AND section and a fixed OR section. Okay. Now so that's what we have is about the idea of this PAL has come from using memory as a programmable logic. Because of non-volatility the PROM was used, and which was a fixed AND programmable OR. Number of AND gates used were less, so we may reduce the number of AND gates, making it programmable, which enable to program the product terms, and that was called PLA. And for a single output, again the moment the AND gates were programmable OR was not very much necessary. So that was prompted the architecture of the PAL, which is nothing but programmable AND and fixed OR. So let us turn now to some real devices. The first device, okay, again the bit of a history, because nobody makes this PAL 16L8 anymore, but if I remember, if I can recollect, this was one of the devices which came into the existence, or people designed 16L8, and then the AMD used to make this particular device. Texas Instruments, this particular the diagram is from the Texas Instruments old data sheet. Okay. So that shows the internal of the device. I mean, don't be kind of alarmed by the number of lines, it's very simple. So I hope you can kind of it's visible. So take this input, this was a 20 pin dual inline package, DIP package, which in today's standard was very huge but hardly implemented very low density logic function. Okay. So take this input, this was an input, you see this one is going through directly through a buffer and through an inverter, that shows a buffer and an inverter together, and two lines. So instead of showing it here to save space, it is shown on the side. So this line number 3, like 2 and 3 are the complement, and the particular line of 1 and 1 bar is these two. So you have another input 2, so that line 2 and the input is here. So these lines are nothing but the inputs are its complements, and so you have a dedicated input 1, 2, 3, 4, 5, 6, 7, 8, 9, and this particular one. So there are 10 dedicated inputs. So you can up to 20, say 0 to 19 up to here is 10 inputs and its complement. Okay. Maybe that some connection may be kind of you can see these two connections are here, but I am just telling the number of lines. 20 lines are for 10 dedicated inputs and its complement, and these AND gates, now you take one of the AND gate here, this has connection to all the inputs which is programmable with some kind of programmability at this junction. Okay. So now if you see there are 0 to 31, so there are 32 vertical lines that that kind of tells us that there are 16 inputs and its complement. Okay, now we have located the 10 inputs. So where does that additional 6 input come? So look at this, maybe look at this structure, we will come to 6 additional input. So here you see there are 1, 2, 3, 4, 5, 6, 7 AND gates permanently connected to an OR gate, which is going through a tri-state inverter and it is available as an output. Okay, and the tri-state inverters enabled is controlled by another AND gate, we can call it a control AND gate. Okay, that means if this AND gate output is high, this output is available, if it is low it is tri-stated. Okay, but so this is a dedicated output which can be enabled or cut off. Similarly come, that's pin 19 and pin 12 is also a dedicated output. So there are, if you see, 1, 2, 3, 4, 5, 6, 7, 8 outputs. So that is what is shown here, 8 output. But and the top one and the bottom one are kind of dedicated outputs. And look at this section 1, 2, 3, 4, 5, 6. You see that it is, when you enable this tri-state gate it acts as an output, but if you cut it off then this acts as an input. Okay, so along with 10 dedicated inputs we have 6 IOs, okay, which can be used as output or input. So this now allows this IO pin to be used as input also. Okay, so in addition to 10 dedicated inputs you have 6 IOs which can be used as input. So there are maximum possible number of input is 10 plus 6. So you have 16 inputs and its complement. So there are 32 vertical lines, that is how the 32 lines come. So now you imagine this, each AND gate has 32 inputs with programmability. So you can choose any of the 16 inputs or its complement to form a product term or a min term or whatever you call. Okay, so and in one section you can have up to 7 product terms. Okay, up to 7. Suppose you can use 3 of them or you can leave the 4 unused. Okay, we will quickly see how it is kind of to be able, I mean how can you disable AND gates. Okay, we will see that, we will in a moment I will tell you. So now you look at this output kind of this dedicated output, there is hardly any reason for a tri-state gate. So most of the time this need to be permanently enabled unless you connect to some kind of a data bus where it is tri-stated or a shared bus or something like that. So how to permanently enable it? So the idea is that basically this is, you cannot, like you have studied the gates and it's a bit ridiculous to think of a kind of 16 input 32 input AND gates. Okay, so definitely this is a wired AND gate. Okay, it's a single line and I hope you have studied wired AND or wired NOR. We will see that, I will show you how it is really implemented, but don't worry, this is not like a conventional kind of TTL circuit with 32 input or not even a conventional CMOS AND gate with 32 input. It's a wired AND or wired OR, we will see that. Okay, so now assume that this is a wired gate with a single line with a resistance pulled up to the VDD or VCC. Okay, now what you do is that to permanently make the output of the AND gate 1, you blow all the connections, you don't remove all the connections, then this input is pulled up, and since the input, all the inputs are 1, the output will be 1, it is permanently enabled. Okay, so that is how the AND gate is permanently enabled. Okay, but there is a need, suppose we have 7 product terms here in a particular, for a particular Boolean function we need only kind of 6 product terms, and we need to kind of disable this AND gate. Okay. Now how to do that is very simple. Okay. You know that A and A bar is 0, the same principle is applied here. What you do is that don't do any programming on this input, retain all the connections. Okay. All 32 connections are retained. Now assume there has to be for some function at least one input has to be there. So even if there is one input, say A is connected here, B is connected here. So for a particular this AND gate, A and A bar is connected to an input. So irrespective of the input is 0 or 1, this AND gate output will be 0 always, and that is disabled. Okay. So you want to use only 3 AND gates, no problem. Rest of the 4 AND gates you retain all the connection, don't do any programming, then those output are disabled. Automatically we are doing the programming of the OR. Okay. By programming the AND gate 0, output 0, we are implementing the programmable OR functionality. So that's the basic idea of how to manage if the number of product terms are less. Okay. That is how it is managed. So now what we do is that to understand it a little more better. Okay. So essentially it was, it was a kind of general purpose programmable device where you connect various input. It really doesn't matter where you connect, and that was the first time something of this was happening. Like you could connect the input lines anywhere. So depending on your PCB design, you could say it was not convenient to bring A here, maybe it was convenient to bring A here, it doesn't matter, you connect it there because you could program it appropriately. So you could connect the various inputs here, various output, and depending on your need you program the number of AND gates and the product terms. Okay. That was what the basic idea. It works as a combination circuit, and we will see how this is used as a the devices which was meant for sequential circuit data path, and though we can't kind of seriously use these kind of simple PLDs for great the data path and things like that was not possible, but still compared to earlier at that time the discrete gates, this was a major leap, major programmability. To that extent the studying this is a very good idea. So now let us come back to the slide. Let us take this kind of say a part of it, maybe we will take this first 3 section a little bit magnified to understand it better. Okay. So that is what is shown, the inputs like 1, 2, 3, 4 inputs. Okay. And 3 output section. Okay. And now this is a dedicated output. Okay. And which we can use it as only as an output. Definitely this can be kind of cut off if it was connected to a shared bus. It was possible to cut off by this control AND gate, that you can permanently cut it off, or you can a product term can control it. Okay. So that was a possibility here, but take this section which is much more interesting. As I said, say this is an output, and mind you there is this is a tri-state inverter. Okay. And this was an active low kind of circuit, and that is how this L comes in the picture, say PAL 16L8. Okay. You might wonder, suppose you have a Boolean function y is some product term, then you implement, if you directly implement that product term here, then what happens is that you will get the y bar instead of y. Okay. That was an issue, but it's very easy. Suppose you have y to be implemented, then you apply De Morgan theorem, you say y bar, then you apply the De Morgan theorem, convert that into equivalent Y bar product terms and you implement it, then you are implementing Y bar at this AND OR gate, so which is inverted by this inverter, then you get the Y, that is how this was used. Okay. So this inverter itself is not a problem because the complement of that was taken and was implemented by the tools. And maybe we are this structure, though it is like this kind of output combined with the input, though it's a very it's a very kind of very simple looking structure, but it has many use. It is really kind of very elegant design. Though it looks very simple, it has lot of advantages. This particular connection, this one connection, we will soon see. Maybe we are coming to the end of this lecture, so I will kind of wind up here because we don't have time to kind of go through that. So in the next lecture we will go through it, but what we have seen is a kind of commercial device then used, now it is not available, which is called PAL16L8 with 16 kind of 10 dedicated inputs, 6 IOs. So the maximum number of inputs was 16, so there are 32 lines, vertical lines, or 32 inputs, 16 inputs and its complement, and there are 2 dedicated outputs. Each OR gate has 7 programmable AND gates. Each AND gate has 32 inputs which can be connected to 16 inputs or its complements. Then there is a tri-state gate at the output of the OR gate tri-state inverter. The enable is controlled by another gate, and we also have seen how to permanently enable that, and there were 7 product terms going to an AND gate, and we have seen suppose you need only 3 AND gates, 3 product terms, how to disable 4 product terms by retaining all the connections which bring in the programmable OR facility in the programmable AND itself. And we will see a little more in detail that IO section of the 16L8 which is very elegant, and then we will move on to some kind of devices with flip flop which allows you to implement data path and sequential circuit. Then pretty much we can move to the at least one device which is probably available even now which can be used in simple PLDs, then we will move on to the complex PLD. So as I said, though it is not useful directly, this will enable us to understand the CPLDs which have some use today. We will be able to understand the architecture of it very nicely if you understand this. So please revise what we have done today, and I wish you all the best.